Something just broke the rules of the solar system. Astronomers have confirmed that 32/Atlas, our third ever interstellar visitor, shifted its orbit in a way that can't be explained by gravity or even by powerful gas jets, contradicting everything we know about how comets move. This 8-m-wide cosmic intruder is flying through at nearly 60 kilometers per second. But the usual suspects, sunlight and outgassing, just don't add up. If gas alone can't explain why 3I/Atlas defied gravity, what invisible force is at work? The stakes for astronomy and for our understanding of what enters our cosmic backyard have never been higher. So, how did this giant break the rule book right in front of humanity's best instruments? July 1, 25. Astronomers at the Atlas Survey spot something that shouldn't exist. An object streaking through the solar system at nearly 60 kilometers per second. That's fast enough to escape the sun's gravity forever and more than double the speed of the last two interstellar visitors. But speed is just the start. 3 Atlas is massive. Estimates put its diameter between 3 and 7 m, making it the largest interstellar object humanity has ever tracked. For perspective, Halley's Comet is just 7 miles across, and it's considered a giant by comet standards. Within hours, observatories worldwide scramble to confirm what's unfolding. The object's orbit isn't just hyperbolic. It's practically a straight shot through the solar system with an eccentricity over 6. That's not just rare, it's unprecedented. The trajectory, the speed, the size, every aspect screams outsider. And as the data pours in, one detail stands out above the rest. As 3I/Atlas barrels toward the inner planets, its path begins to veer. Not wildly, not in a way you'd notice with the naked eye, but enough to set off alarms among the world's best orbital modelers. Here's where things get uncomfortable. The usual suspects, gravity, solar radiation, even the powerful jets of gas that can nudge a comet off course, can't fully account for what's happening. We're watching a cosmic heavyweight, a body with the mass to shrug off most forces, shift its orbit in ways that just don't add up. The math is off. The rule book, the one that's governed every comet and asteroid we've ever seen, suddenly looks incomplete. For astronomers, this isn't just a curiosity. It's a crisis. If something this big, this fast, can break the rules right in front of our best instruments, what else might slip through undetected? What else might we be missing? The stakes aren't abstract. They're about the limits of our knowledge and what it means when the universe throws us a curveball we can't explain. So, if you're the kind of person who wants to see the rulebook challenged, who wants to watch science catch up to the cosmos, now's the time to hit subscribe because the story of 3I/Atlas is just getting started. And the next chapter could change everything we thought we knew about what moves through our cosmic backyard. Comets don't just coast through the solar system on rails. Their journeys are shaped by a constant tug-of-war between gravity and something far less predictable, outgassing. Picture a comet as a dirty snowball, frozen hard until sunlight hits. As it draws closer to the sun, ice trapped inside begins to vaporize. Gas jets erupt from the surface, sometimes in spectacular geysers, sometimes as subtle leaks. Each jet acts like a tiny thruster, nudging the comet this way or that. The effect is a bit like letting go of a balloon and watching it zip around the room, propelled by its own escaping air. Astronomers have spent decades turning this chaos into math. The Rosetta mission to Comet 67P/Churyumov-Gerasimenko proved just how powerful these jets can be. Rosetta watched as only about 10% of 67P's surface did most of the work, firing out plumes that not only changed the comet's path, but actually spun the entire nucleus faster or slower depending on which jets were active. With every orbit, these outbursts add up, shifting the comet's trajectory by measurable amounts. In fact, orbital models must include these non-gravitational forces, or predictions quickly go off track. The rules are simple in theory. The more gas a comet releases and the faster it escapes, the bigger the push. Scientists measure the amount of material, often in kilograms/s, flying off the comet and use it to calculate the force. For a typical comet, water ice does the heavy lifting, turning to vapor and blasting dust away at hundreds of meters/s. The result? A slow, steady drift from the path gravity alone would dictate. Over time, even a small, persistent push can move a comet thousands of kilometers off its predicted course. But there's a catch. The effect depends on the comet's mass. A small, lightweight nucleus is easy to budge. A large, dense one is stubborn, requiring much more force to achieve the same shift. That's why the details, how much gas, how quickly, and from where on the surface matter so much. Every significant comet in history from Halley to 67P has obeyed this rulebook. If you know the jets and the mass, you can predict the motion. This is the playbook astronomers reach for every time a new comet appears. Gravity sets the stage, but outgassing writes the footnotes. For most comets, the math checks out. The jets explain the drift, the models predict the path, and the universe behaves as expected. With 32/Atlas, though, that's about to be put to the test. Orbital prediction is supposed to be a solved problem. Plug in the numbers. Mass, velocity, solar gravity, planetary tugs, and the path of any comet or asteroid should trace out with pinpoint accuracy. For 3I/LOS, the numbers refuse to cooperate. The calculated trajectory with an eccentricity of 6.141 sketches a nearly straight line through the solar system. A geometry that's rare enough to make even seasoned dynamicists pause. But it's what happens when you overlay the predicted path with the actual data that exposes the crack in the system. Each new observation comes with a timestamp, a set of coordinates, and a margin of error. Stack 100 of these and a pattern should emerge, one that matches the equations not just in theory but in the real sky. Instead, the residuals, the tiny differences between where 3I/Atlas should be and where it actually is, begin to drift. Not by much, not enough to shout, but enough that the overlay doesn't quite snap into focus. For a normal comet, these gaps are quickly closed by adjusting for gas jets or dust ejection. With 3I/Atlas, those corrections fall short. The magnitude of the offset can't be erased with the usual suspects. The path veers almost imperceptibly, but in a way that persists across datasets and observatories. Engineers and orbital modelers run the numbers again. They factor in every known variable, the sun's pull, planetary perturbations, even the subtle push of solar radiation. The result is always the same. The model can't fully capture the deviation. The geometry of the anomaly is clear on the residual plots. The object's actual position diverges from prediction, not in random scatter, but in a systematic way that suggests a force at work outside the standard playbook. This isn't the kind of error you can blame on bad data or a misaligned telescope. The global network of observatories from Mount Aya to La all report the same subtle offset. The high eccentricity path of 3Ma/Atlas, so clean and direct in simulation, now carries a visible scar, a gap between theory and reality that no one can close. For the first time, the orbit itself becomes the main character, refusing to play by the rules. The chemistry of the coma and the physics of outgassing are next in line for scrutiny. But the immediate problem is right there in the geometry. The rule book doesn't fit. The coma of 3/Atlas is not just a halo of light. It's a chemical fingerprint. And that print is unlike anything seen in the solar system. The numbers coming from the James Webb Space Telescope are impossible to ignore. For every molecule of water vapor in its coma, there are 8 molecules of carbon dioxide. That's an 8-to-1 carbon dioxide to water ratio, off the charts, even compared to the weirdest Oort cloud comets. Most comets are water-dominated with carbon dioxide playing a supporting role. Here, carbon dioxide calls the shots. It's pouring off the nucleus at rates measured around 129 kilograms per second, dwarfing the 6.6 kilograms per second for water. In theory, more gas means more push. Outgassing acts like a set of thrusters, each molecule a tiny kick. But even adding up every molecule, the math falls short. For an object this massive, estimates put the nucleus between 3 and 7 miles across. These jets don't have the horsepower to explain the observed drift. The momentum just isn't there. The chemical oddities don't stop with gas. Spectroscopy from the Very Large Telescope picks up something stranger, 22 distinct emission lines from atomic nickel, but iron is nowhere to be found. That's not normal. Nickel and iron usually travel together in cosmic materials, forged side by side in supernovae and mixed in meteorites. Here, nickel is out on its own, released into the coma by a process that seems to favor it over iron, possibly from exotic organometallic complexes or nanograins that break down under solar heating. The nickel production rate at about 4.7*10 to the power of 22 atoms per second is steeply sensitive to distance from the Sun, ramping up as 3/Atlas gets closer. Even the dust output doesn't tip the scales. Hubble data shows a dust mass loss rate between 6 and 60 kilograms per second. Significant, but not enough to account for the kind of orbital deviation being mapped by astrometric teams. The jets are active. The coma is thick with carbon compounds. And yet, for all this chemical drama, the object's path still refuses to line up with the numbers. The natural engine is running, but it's not moving the needle far enough. The evidence is piling up. Gas alone can't do the job. Something is missing from the standard playbook. 6 years ago, astronomers faced a puzzle that still haunts the field. Oumuamua. That object, barely 400 meters across, shot through the solar system in 2017, moving fast enough to escape forever. But speed wasn't the real shock. As the data came in, something impossible happened. Oumuamua's path bent ever so slightly, away from what gravity alone could explain. Not a wild swerve, but a tiny persistent push. The numbers didn't lie. The residual acceleration, about 17 millimeters per second squared, was real. Yet there was no visible coma, no jets, no dust, just a dry, tumbling shard, accelerating as if nudged by an invisible hand. The headlines came fast. Interstellar visitor accelerates mysteriously. Comet or something else. Theories piled up. Some argued for outgassing, maybe hydrogen, maybe something we'd never seen before. Others suggested radiation pressure or even something engineered. But the truth was simpler and more unnerving. There was no clear culprit. Every model left a gap. Now with 3I/Atlas, the sense of déjà vu is hard to ignore. Here's another outsider, this time orders of magnitude larger, showing hints of the same rule-breaking behavior. The difference is scale. A 7m-wide object isn't supposed to drift off course so easily. For Oumuamua, a wisp of gas might have done it. For Atlas, the force required is staggering. Yet, astronomers are watching their models unravel again, residuals stacking up in ways that echo 2017's anomaly. What started as a one-off is starting to look like a pattern. Interstellar objects aren't just rare, they're unpredictable. They don't just visit, they rewrite the rules. The shock isn't just that Atlas is drifting. It's that for the second time, gravity alone can't keep the universe on script. Picture the sheer bulk of 3/loss. This isn't a pebble drifting through space. It's a cosmic boulder with mass estimates running thousands of times greater than Oumuamua. The numbers are staggering. Even at the low end, you're looking at a nucleus with several billion tons of inertia. To nudge something like that off course, you'd need a force that dwarfs what most comets ever experience. For comparison, the Rosetta mission measured jets on Comet 67P that could move a mountain-sized chunk by a few kilometers per orbit. But 3/Atlas is in a whole different weight class. Its mass soaks up momentum like a bowling ball in a sea of ping-pong balls. Every molecule of gas it throws off barely registers. A whisper against a freight train. The usual comet math says more mass, less motion from outgassing. So when orbital modelers see this giant shifting its path in ways the equations can't balance, the problem isn't subtle. The push required to explain the drift would demand outgassing on a scale that just isn't there. Even if every square inch of the surface was erupting, the total force still falls short. This isn't just a matter of tweaking the numbers. The entire momentum budget comes up empty. For an object this massive to move, something big has to be pushing. And right now, all the usual suspects are coming up light. Every established explanation for 3I/Atlas's drift gets stress-tested. And every time, something doesn't quite fit. If all the usual gas jets and dust outflows can't move this much mass, what's left? Some astronomers point to fragmentation. Maybe a hidden crack split open, shifting the center of mass just enough to nudge the orbit. But there's no evidence for a major breakup. Others wonder if the nucleus is less dense than it appears, a loose rubble pile instead of a solid boulder. But the COMAS chemistry doesn't back that up either. Then there's the wild card. Harvard's Abbie Loeb and a handful of contrarians have floated a possibility that sounds like science fiction. What if Atlas is being pushed by something more exotic? Loeb's 23 paper sketches out a scenario where a thin ultralight sail, think a solar sail but on a cosmic scale, could ride on sunlight alone, producing a force too subtle for our current models to catch. The numbers work for Oumuamua, which was tiny and light. For Atlas, with its bulk, the math gets harder but not impossible if the object is hollow or engineered for maximum surface area. No one in the mainstream is calling Atlas artificial. But the fact that these ideas are even on the table says something about how far this object is pushing the boundaries. When gas can't explain the motion, physics demands another answer, natural or not. Each failed explanation turns up the volume on the question, what exactly are we looking at? And if our models can't handle Atlas, what else out there might be slipping through the cracks? The next chapter in this story is already taking shape. The Vera C. Rubin Observatory, with its 10-year legacy survey of space and time, is about to change everything we know about interstellar visitors. When Rubin comes online, astronomers expect to spot dozens of these objects every year, maybe even more. That means 3/loss isn't a once-in-a-lifetime event. It's the beginning of a flood. For the first time, we'll have a steady stream of messengers from other star systems, each carrying clues about where and how they formed. Every new detection brings a chance to catch another rule breaker, another cosmic outlier that doesn't fit the script. But here's the catch. If our models can't even keep up with Atlas, what are we missing from the ones that slip by undetected? The universe isn't just throwing curveballs. It's pitching blindfolded, and we're still learning how to swing. Each anomaly is a reminder that our grip on the cosmos is only as strong as our ability to question it. The more we look, the less the universe seems willing to play by our rules. So, why does any of this matter? Because these objects aren't just passing rocks. They're time capsules from other suns carrying the chemistry and history of worlds we'll never visit. If we want to understand our place in the galaxy, we have to chase every mystery, every unexplained orbit, every outlier that blurs the line between natural and engineered. The next discovery could rewrite everything. If you want to be there when it happens, hit subscribe and tell us, what do you think 3I/LOS really is? On July 1, 2025, astronomers confirmed the arrival of 3I/LOS, an interstellar object traveling nearly 60 kilometers per second with a nucleus up to 7 miles wide. Its path was tracked by NASA and the ESA, revealing an orbital shift that standard models of comet physics could not explain. Observations from the James Webb Space Telescope showed a carbon dioxide to water ratio of 8:1 and nickel present without iron, setting it apart from all known solar system comets. Despite decades of accurately modeling comet motion using gas outgassing, the forces measured here were far too weak to account for the deviation. Just as with Oumuamua in 2017, the scientific record now holds another case where gravity and jets alone fall short. What drives these anomalies remains unknown. No consensus has been reached and key data are still under review. As sky surveys prepare to detect dozens more interstellar visitors each year, one fact is clear. The rule book for cosmic intruders is not yet complete. Subscribe to stay updated as we uncover what these objects could reveal.